Welcome to The Explainer. Today, we're stepping into the super dynamic, absolutely fascinating world of chemical kinetics. You know, chemistry, by its very nature, is all about change. We're looking at how substances transform, sure, but more importantly, we're looking at the speed of that transformation. We're going to break down the invisible, microscopic collisions that literally govern everything around us, from how fast your leftovers spoil in the fridge to exactly how fuel burns in your car's engine.
Okay, let's dive into this. We've all heard the classic saying, right? Diamonds are forever. But from a strict chemical standpoint, are they really? Well, thermodynamics actually says no, they aren't. It predicts that diamond will eventually convert into graphite. It's a thermodynamically favorable reaction. But don't panic. Your jewelry isn't going to turn into pencil lead anytime soon. Why? Because the conversion rate is so incredibly imperceptibly slow. So thermodynamics tells us if a reaction can happen. But kinetics tells us it'll take virtually forever to actually do it.
Here's our quick roadmap for today. We'll start with 1, the speed of change, then move into 2, measuring reaction rates. After that, it's 3, rate law and reaction order, followed by 4, elementary versus complex reactions. Then we'll wrap up with 5, molecularity of a reaction, and finally, 6, energy, catalysts, and collisions.
All right, let's jump right into section 1, the speed of change.
To really get a grip on chemistry, you kind of need to view it through two lenses, thermodynamics and kinetics. Think of thermodynamics as the bouncer at the club door. It determines the feasibility of a chemical reaction, telling us if it's even allowed to happen. But chemical kinetics? That's the stopwatch. Derived from the Greek word kinesis, which means movement, kinetics determines the actual speed or rate of a reaction once it gets the green light to start.
Out in the real world, this speed varies massively. We generally see 3 main speeds for chemical reactions. First up, instantaneous reactions. These are lightning fast, like the ionic precipitation of silver chloride when you mix aqueous solutions of silver nitrate and sodium chloride. It happens in a literal flash. Second, we've got slow reactions, like the rusting of an iron gate exposed to air and moisture over months or even years. And finally, moderate reactions. A good example here is the inversion of cane sugar or the hydrolysis of starch, which tick along at a nice, steady, measurable pace.
Moving right along to section 2, measuring reaction rates.
So how do we actually define this? Well, the reaction rate is simply the change in concentration of a reactant or a product in unit time. You can basically measure this in one of 2 ways. You can either track the rate of decrease in the concentration of your reactants as they get used up in the reaction, or you can track the rate of increase in the concentration of your products as they're being formed. It's 2 sides of the same coin.
But, as they say, timing is everything. Just like driving a car, there are 2 distinct ways to look at speed. The average rate is kind of like calculating your overall speed for a long road trip. You're measuring it over a broad, macroscopic period of time. The instantaneous rate, on the other hand, that's like glancing down at your speedometer at 1 exact, precise second. It's the rate of the reaction at one specific, infinitesimal moment in time. Both are absolutely crucial for different types of kinetic analysis.
Now, what's really interesting about the data here is how the rate actually shifts as the reaction progresses. Check out the numbers for the hydrolysis of a reactant over time. At 0 seconds, our reactant concentration is sitting at 0.100. By 50 seconds, it's dropped to 0.0905, giving us an average rate of 1.90 mil. But look at what happens between 50 and 100 seconds. The concentration keeps dropping, sure, but our average rate also decreases to 1.70. This perfectly illustrates that the rate of a reaction generally decreases as time goes on, simply because the concentration of reactants is dropping. This slowing down is exactly why chemists often measure a reaction's half-life. You know, the specific amount of time it takes for exactly half of the initial reactant to be completely consumed.
Let's see how this builds as we move to section 3, rate law and reaction order.
This brings us to the absolute golden rule of chemical kinetics. Representing the rate of a reaction in terms of reactant concentration is what we call the rate law. But here's the catch, and it's a big one. You cannot just look at a balanced chemical equation and theoretically guess the rate law. You just can't. The exponents in a rate law often don't match up at all with the stoichiometric coefficients in the balanced equation. It literally must be determined experimentally in a lab.
Okay, so once you've gone to the lab and experimentally determined that rate law, you can figure out the reaction order. The order of a reaction is defined as the sum of the powers or the exponents of the concentration of the reactants in that specific rate law expression. Essentially, what the reaction order tells us is exactly how sensitive the speed of the reaction is to any changes in the concentration of our reactants.
Reaction order has some pretty quirky characteristics too. The overall order can be 0, 1, 2, or 3. Amazingly, it can even be a fraction. But what's probably most fascinating to me is a zero-order reaction. If a reaction is zero order, it means the rate is completely 100% independent of the concentration of the reactants. You could dump a massive amount of extra reactant in there, and the reaction wouldn't speed up even a tiny bit. To track these specific orders over time, chemists use these things called integrated rate equations. And as you might guess, they look vastly different for a zero-order reaction compared to, say, a first-order one.
Up next is Section 4, Elementary versus Complex Reactions.
So a balanced chemical equation almost never gives us the true, behind-the-scenes picture of how a reaction actually takes place. Why? Because it is incredibly rare for a reaction to get totally completed in just one simple step. Now, reactions that do happen in a single step are called elementary reactions. But in the real world, most of the time we're looking at a sequence of multiple elementary steps chained together. We call the whole shebang complex reactions.
And this brilliantly illustrates how complex reactions work. Just think of a relay race. Your team's chances of winning aren't based on your fastest runner, right? They're completely dependent upon the slowest person on the team holding the baton. It's the exact same in chemistry. If a complex reaction takes place in several steps, the overall rate of the entire reaction is totally controlled by the slowest step. Chemists literally call this the rate-determining step.
Moving down to the microscopic level with Section 5, Molecularity of a reaction.
To really understand the mechanics of a reaction, we use a concept known as molecularity. This is simply the number of reacting species, and that could be atoms, ions, or whole molecules, taking part in an elementary reaction. These species must literally crash into each other and smash together simultaneously in order to actually bring about a chemical change.
Because this relies on literal physical collisions, molecularity is strictly categorized. A reaction can be unimolecular, which involves just one reacting species decomposing or changing. It can be bimolecular, which means a simultaneous collision between two species. Or it can be trimolecular, involving three. But I should point out, trimolecular reactions are super rare and usually very slow. Think about it. The probability that more than 3 separate molecules can all collide with each other at the exact same moment in the exact right way, it's incredibly small.
So the crucial point here is understanding the stark difference between reaction order and molecularity. Order is a purely experimental quantity, whereas molecularity is a theoretical concept based on these physical collisions. Because of this, order can be zero or fraction. But since you can't have 0 molecules colliding, or half a molecule colliding, molecularity has to be a whole integer of 1, 2, or 3. Finally, while reaction order applies to the entire complex reaction, molecularity really only has meaning for single elementary steps.
All right, let's wrap this up with Section 6, Energy, Catalysts, and Collisions. See, just bumping into each other isn't quite enough. Molecules need a certain minimum amount of energy to react, which we call activation energy. Think of it as a massive, steep hill the molecules have to climb over to turn into products. So what does a catalyst actually do? Well, adding just a tiny amount of a catalyst can massively speed up a reaction because it provides an alternate pathway. It essentially carves a tunnel straight through that hill, lowering the activation energy barrier so a lot more molecules can easily make it to the other side. By the way, this whole energy barrier thing and how it changes in temperature help molecules overcome it is beautifully modeled mathematically by the famous Arrhenius equation.
And that brings us to the ultimate summary, collision theory. For a chemical reaction to actually happen in the real world, 2 very strict requirements have to be met during a collision. First, the molecules must smash into each other with sufficient kinetic energy to overcome that activation energy barrier we just talked about. Second, they must hit each other in the exact proper orientation, which chemists call the steric factor. If they have the energy but happen to hit backwards, or if they have the perfect orientation but lack the energy, they just bounce harmlessly off each other. Without both conditions being met, collisions simply do not lead to a reaction.
We've traveled all the way from observing rust on an old car down to the exact angle 2 invisible molecules need to crash into one another. It's honestly fascinating that the entire visible world is dictated by these tiny, instantaneous microscopic events.
If controlling molecular collisions determines whether our food spoils or our engines run, how else can mastering chemical kinetics allow us to master the macro world around us? Think about it. Thanks so much for joining me on this explainer, and keep exploring the science of change.